Now let's look at number of particles, Avogadro's number, and number of moles. Alright, in our previous study we understand a bit about the number of mole, and I also mentioned that number of mole can be referred back to this formula as mass in gram divided by molar mass. So this molar mass would have the unit of gram per mole, while this one will have gram, so gram divided by gram per mole, you get mole here. So that's pretty obvious. And this molar mass, actually the value are the same as the relative atomic mass, molecular mass, and formula mass. Okay, but of course we need to be clear about certain terminology. So it's number of mole equals to mass over molar mass. You can also think of mole as a ratio of actual mass to the standard mass. Actual to the standard. Alright, what can we say from here? We can see some facts occurring here. For example, when I say ratio of actual to standard, it's mass over the standard, molar mass. Alright, this is the actual one, this is the standard one. Alright, so now we are interested to find out that in 1 mole, how many number of particles are there actually. So 1 mole, according to the scientist who discovered this, Avogadro, and this is called Avogadro's number, it has 6.02 times 10 power 23 particles. When we say particles, we could mean atoms, molecules, or ions. Let's just talk about atoms first. Alright, so we have 6.02 times 10 power 23 atoms. If you line up all these dots side by side, if you line them up in straight line, and there are 6.02 times 10 power 23 of them together, you can actually construct the radius of galaxy. Okay, so that is how huge the amount is. But even though huge amount, but the size is too small, extremely small. Alright, they can even stack up the whole United States of America. Let's say this is a map of America. So you can actually stack up all this using the soda can, or stack them up one by one, and can fill up the whole country if you have 6.02 times 10 power 23 soda can. Alright, so this is how huge the amount is. So now back to what we have discussed so far. One of the standard that they put forward is 1 mole of substance will definitely have 6.02 times 10 power 23 particles. To help us to use the actual over standard example again, we can actually put this actual number of particle over the standard number of particle. This is Avogadro's number. And this Avogadro's number is 6.02 times 10 power 23. You'll be using this constant all the time. And as I mentioned before, from this formula I can say number of particle, the actual number of particle, is actually number of mole times the Avogadro's constant. Okay, let's start a new page to see this clearer. N equals to N and A. Just now we proposed that 1 mole would have 6.02 times 10^23. I put a dot. What if it is 2 mole? 2 mole, it would have 2 times 6.02 dot dot dot. What if it is 17 mole? Then you have 17 times 6.02 dot dot dot. So you realize that each time I put forward different mole, I must use this mole to multiply the constant. That's why I come up with this formula. Of course, I didn't come up with this formula myself. I didn't invent it. I just put forward this simplistic formula for you to follow. You can either use this to describe that this is the actual number of particles in the container. Okay, it could be more than the Avogadro's constant. It could be more than 6.02 times 10 power 23 if you have more than 1 mole. Alright, so this is just depending on the number of mole you have. It could be 1, it could be 2. If it's 1, it's just the same. If it's 2, 2.5, 2.7, and this is the Avogadro's constant. And I also mentioned before, if you want to look at it another way, that would be number of mole. Again, is a case of actual over standard, the same as actual mass over standard mass. Later on, you'll find out that you might be using these 4 parameters altogether to find the mass of the particle. Alright?